एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज मैं करने जा रही हूँ यूनिट 5 स्टेट्स ऑफ मैटर। तो आप लोगों की जैसे रिक्वेस्ट आ रही है ऑडियो बुक्स के लिए, मैं उस हिसाब से ही चैप्टर प्रिपेयर कर रही हूँ और मेरी प्रायोरिटी ये है कि थ्योरेटिकल चैप्टर्स को मैं पहले कवर कर लूँ। तो आप लोग कमेंट सेक्शन में मुझे अपने चैप्टर्स बताते जाइएगा। ऑल्दो आई विल कंप्लीट बिफोर नीट एग्जाम ऑल दी केमिस्ट्री चैप्टर्स सो दैट यू कैन डू योर रिविजन एट योर बेस्ट, राइट। बट थोड़ा सा टाइम लगेगा रिकॉर्ड करने में। सो चलिए टाइम वेस्ट नहीं करते हैं और शुरू करते हैं। स्टेट्स ऑफ मैटर। द स्नोफ्लेक फॉल्स येट लेज नॉट लॉन्ग इट्स फेदरी ग्रास्प ऑन मदर अर्थ ere sun returns it to the vapor whence it came or to water tumbling down the rocky slope. रॉड ओ कॉर्नर ने दिया था ये। Introduction. In previous unit we have learned about the properties related to single particle matter and much as atomic size, ionization enthalpy, electronic charge, density, molecular shape and polarity, etc. Most of the observable characteristics of chemical system with which we are familiar represent bulk properties of matter, that is, the properties associated with a collection of large number of atoms, ions and molecules. For example, an individual molecule of a liquid does not boil but the bulk boils. Collection of water molecules have wetting properties. Individual molecules do not wet. Water can exist as ice, which is as solid. It can exist as liquid, or it can exist in the gaseous state as water vapor or steam. Physical properties of ice, water and steam are very different. In all the three states of water, chemical composition of water remains the same, that is H2O. Characteristics of the three states of water depend on the energies of the molecules and on the manner in which water molecules aggregate. Same is true for the substances also. Chemical properties of a substance do not change with the change of its physical state, but rate of chemical reaction do depend upon the physical state. Many times in calculation, while dealing with data of experiments, we require knowledge of the state of matter. Therefore, it becomes necessary for a chemist to know the physical laws which govern the behavior of matter in different states. In this unit, we will learn more about these three physical states of matter, particularly liquid and gaseous states. To begin with, it is necessary to understand the nature of intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles, because a balance between these determines the state of a substance. 5.1 Intermolecular Forces. Intermolecular forces are the forces of attraction and repulsion between interacting particles, that is atom and molecules. This term does not include the electrostatic forces that exist between the two oppositely charged ions and the forces that holds atom of a molecule together, that is covalent bond. Attractive intermolecular forces are known as Wanderwall Forces, in honor of Dutch scientist Johannes van der Waals 1837 to 1923, who explained the aviation of real gases from the ideal behavior through these forces. We will learn about this later in this unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole-dipole forces and dipole-induced dipole forces. A particularly strong type of dipole-dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bonding, or you can say in hydrogen bond formation. Therefore, it is treated as a separate category. We have already learnt about this interaction in Unit 4. At this point, it is important to note that attractive forces between an ion and a dipole are known as ion-dipole forces, and these are not van der Waals forces. We will now learn about different types of van der Waals forces. 5.1.1 Dispersion forces or London forces. Atoms and nonpolar molecules are electrically symmetrical and have no dipole moment because their electronic charge cloud is symmetrically distributed. But a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close vicinity of each other, figure 5.1a. It may, here you can see this diagram 5.1a. It may so happen that momentarily electronic charge distribution in one of the atoms, say A, becomes unsymmetrical, that is, the charge cloud is more on one side than the other. Figure 5.B and C. This results in the development of instantaneous dipole on the atom A for a very short time. Here you can see the diagrams 5.1A, 5.1B and 5.1C. This instantaneous or transient dipole distorts the electron density of the atom B, which is close to it, as consequence a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. Similarly, temporary dipoles are induced in molecule also. This force of attraction was proposed by the German physicist Fritz London. And for this reason, force of attraction between two temporary dipole is known as London force. Another name for this force is dispersion force. These forces are always attractive and interaction energy is inversely proportional to the sixth power of the distance between the two interacting particles, that is 1 upon r to the power 6, where r is the distance between two particles. These forces are important only at short distances, that is approximately 500 picometer, and their magnitude depends on the polarizability of the particle. 5.1.2 Dipole-Dipole Forces. Dipole-dipole forces act between the molecules possessing permanent dipole. Ends of the dipole possesses partial charges, and these charges are shown by Greek letter delta. Partial charges are always less than the unit electronic charge 1.6 into 10 to the power minus 19, and the polar molecules interact with neighboring molecules. Figure 5.2a shows electron cloud distribution in the dipole of hydrogen chloride, and figure 5.2b shows dipole-dipole interaction between two HCl molecules. I will show you diagram later. This interaction is stronger than the London force but is weaker than ion-ion interaction because only partial charges are involved. The attractive force decreases with the increase of distance between the dipoles. As in the above case, here also the interaction energy is inversely proportional to distance between polar molecules. Dipole-dipole interaction energy between stationary polar molecule, as in solids, in proportional to 1 upon r cube, and that between rotating polar molecule is. Now you can see 5.2a diagram, that is the distribution of electron cloud in HCl, a polar molecule, and B diagram is dipole-dipole interaction between two HCl molecule. Come to the next slide. Proportional to 1 upon r to the power 6, where r is the distance between polar molecules. Besides dipole-dipole interaction, polar molecules can interact by London forces also. Thus, cumulative effect is that the total of intermolecular forces in polar molecules increase. 5.1.3 Dipole-induced dipole forces. This type of attractive forces operate between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Permanent dipole of the polar molecule induces dipole on the electrically neutral molecule by deforming its electronic cloud. Thus, an induced dipole is developed in the other molecule. In this case, also interaction energy is proportional to 1 upon r to the power 6, where r is the distance between the two molecules. Induced dipole moments depends upon the dipole moment present in the permanent dipole and polarizability of the electrically neutral molecule. We have already learnt in Unit 4 that molecules of larger size can be easily polarized. High polarizability increases the strength of attractive interactions. Here you can see 5.3 dipole-induced dipole interaction between permanent dipole and induced dipole. In this case, also cumulative effect of dispersion forces and dipole-induced dipole interaction exist. 5.1.4 Hydrogen bond. As already mentioned in section 5.1, this is a special case of dipole-dipole interaction. We have already learnt about this in Unit 4. This is found in the molecules in which highly polar NH, OH and HF bonds are present. Although hydrogen bonding is regarded as being limited to nitrogen, oxygen and fluorine, but species such as chloride negative may also participate in hydrogen bonding. Energy of hydrogen bond varies between 10 to 100 kJ per mole. This is quite a significant amount of energy. Therefore, hydrogen bonds are powerful force in determining the structure and properties of many compounds, for example, proteins and nucleic acids. Strength of the hydrogen bond is determined by the Coulombic interaction between the lone pair electrons of the electronegative atom of one molecule and the hydrogen atom of other molecule. Following diagram shows the formation of hydrogen bond. Here you can see intermolecular forces discussed so far are all attractive. Molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsion between the electron clouds and that between the nuclei of two molecules comes into play. Magnitude of the repulsion rises very rapidly as the distance separating the molecule decreases. This is the reason that liquids and solids are hard to compress. In these states, molecules are already in close contact. Therefore, they resist further compression as that would result in the increase of repulsive interactions. 5.2 Thermal energy. Thermal energy is the energy of body arising from motion of its atoms or molecules. It is directly proportional to the temperature of the substance. It is the measure of average kinetic energy of the particles of the matter and is thus responsible for movement of particles. This movement of particles is called the thermal motion. 5.3 Intermolecular forces versus thermal interaction. We have already learned that intermolecular forces tend to keep the molecules together, but thermal energy of the molecules tends to keep them apart. Three states of matter are the results of balance between intermolecular forces and the thermal energy of the molecules. When molecular interactions are very weak, molecules do not cling together to make liquid or solid unless thermal energy is reduced by lowering the temperature. Gases do not liquefy on compression only. All the molecules come very close to each other and intermolecular forces operate to the maximum. However, when thermal energy of molecule is reduced by lowering the temperature, the gases can be very easily liquefied. Predominance of thermal energy and the molecular interaction energy of a substance in three states is depicted as follows. Here you can see gas to liquid and liquid to solid. Predominance of intermolecular interaction, and here you can see solid to liquid and liquid to gas. Predominance of the thermal energy. We have already learned the cause for the existence of the three states of matter. Now we will learn more about gaseous and liquid states and the laws which govern the behavior of matter in these states. We shall deal with the solid state in class 12th. 5.4 The gaseous state. This is the simplest state of matter. Throughout our life, we remain immersed in the ocean of air, which is a mixture of gases. We spend our life in the lowermost layer of the atmosphere called troposphere, which is held to the surface of the earth by gravitational force. The thin layer of atmosphere is vital to our life. It shields us from harmful radiations and contains substances like dioxygen, dinitrogen, carbon dioxide, water vapor, etc. Let us now focus our attention on the behavior of substances which exist in the gaseous state under normal conditions of temperature and pressure. A look at the periodic table shows that only 11 elements exist as gases under normal condition. Figure 5.4. Here you can see the diagram. Here you can see all the 11 elements that exist as gases. The gaseous state is characterized by the following physical properties. Gases are highly compressible. Gases exert pressure equally in all directions. Gases have much lower density than the solids and liquids. The volume and the shape of gases are not fixed. These assume volume and shape of the container. Gases mix evenly and completely in all proportions without any mechanical aid. Simplicity of gases is due to the fact that the forces of interaction between their molecules are negligible. Their behavior is governed by some same general laws, which were discovered as a result of their experimental studies. These laws are relationship between measurable properties of gases. Some of these properties like pressure, volume, temperature, and mass are very important because relationship between these variables describe state of the gas. Interdependence of these variables leads to the formulation of gas laws. In the next section, we will learn about gas laws. 5.5 The gas laws. The gas laws which we will study now are the result of research carried on several centuries on the physical properties of gases. The first reliable measurement on properties of gases was made by Anglo-Irish scientist Robert Boyle in 1662. The law which he formulated is known as Boyle's Law. Later on, attempts to fly in air with the help of hot air balloons motivated Jacques Charles and Joseph Louis Galluzak to discover additional gas laws. Contribution from Avogadro and other provided lot of information about gaseous state. 5.5.1 Boyle's Law, that is pressure volume relationship. On the basis of experiment, Robert Boyle reached to the conclusion that at constant temperature, the pressure of a fixed amount, that is the number of moles N, of gas varies inversely with its volume. This is known as Boyle's Law. Mathematically, it can be written as P is proportional to 1 upon V at constant T and N. And now P is equals to K1 1 upon V. This is the equation 5.2, where K1 is the proportionality constant. The value of constant K1 depends upon the amount of gas, temperature of the gas, and the units in which P and V are expressed. On rearranging equation 5.2, we obtain PV is equals to K1, that is 5.3 equation. It means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant. If a fixed amount of gas at constant temperature T occupying volume V1 at pressure P1 undergoes expansion, so that volume becomes V2 and pressure becomes P2, then according to Boyle's law, P1 V1 is equals to P2 V2 is equals to constant, and this is the equation number 5.4. So P1 upon P2 is equals to V2 upon V1. Now you can see this graph 5.5a, graph of pressure P versus volume V of a gas at different temperature. And here you can see the next graph 5.5b, graph of pressure of a gas P versus 1 upon V. Here you can see the table 5.1, the effect of pressure on the volume of 0.09 mole CO2 gas at 300 Kelvin. Figure 5.5 shows two conventional ways of graphically representing Boyle's law. Figure 5.5a is the graph of equation 5.3 at different temperatures, and the value of K1 for each curve is different because for a given mass of gas, it varies only with temperature. Each curve corresponds to a different constant temperature and is known as isotherm, that is constant temperature plot. Higher curves correspond to higher temperature. It should be noted that volume of the gas doubles if pressure is halved. Table 5.1 gives effect of pressure on volume of 0.09 mole of CO2 at 300 Kelvin. Figure 5.5b represents the graph between P and 1 upon V. It is a straight line passing through origin. However, at high pressure, gases deviate from Boyle's law, and under such condition, a straight line is not obtained in the graph. Experiments of Boyle in a quantitative manner prove that gases are highly compressible because when a given mass of a gas is compressed, the same number of molecules occupy a smaller space. This means that gases become denser at high pressure. A relationship can be obtained between density and pressure of a gas by using Boyle's law. By definition, density D is related to the mass m and the volume V by the relation D is equals to m upon V. If we put value of V in this equation from Boyle's law equation, we obtain the relationship. D is equals to m upon K1, bracket close, P is equals to K dash P. This shows that at a constant temperature, pressure is directly proportional to the density of a fixed mass of the gas. Here you can see the problem 5.1. Now 5.5.2 Charles' law, that is temperature volume relationship. Charles and Galluzak performed several experiments on gases independently to improve upon hot air balloon technology. Their investigation showed that for a fixed mass of a gas at constant pressure, volume of a gas, increasing temperature and decrease on cooling. They found that each degree rise in temperature, volume of a gas increases by 1 upon 273.15 of the original volume of the gas at 0 degrees Celsius. Thus, if volumes of the gas at 0 degrees Celsius and T degrees Celsius are V0 and Vt respectively, then Vt is equals to V0 plus T upon 273.15 multiplied V0. And now Vt is equals to V0 in bracket 1 plus T upon 273.15. So Vt is equals to V0 bracket 273.15 plus T upon 273.15. At this stage, we define a new scale of temperature such that T degree Celsius on new scale is given by T is equals to 273, that is capital T, is equals to 273.15 plus small t, and 0 degree Celsius will be given. So T0 is equals to 273.15. This new temperature scale is called Kelvin temperature scale or absolute temperature scale. The 0 degree Celsius on the Celsius scale is equal to 273.15 Kelvin at the absolute scale. Note that degree sign is not used while writing the temperature in absolute temperature scale, that is Kelvin scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific works. Thus, we add 273, that is more precisely 273.15 to the Celsius temperature to obtain temperature at Kelvin cycle or Kelvin scale, If we write Tt is equals to 273.15 plus a small t and T0 is equals to 273.15 in the equation 5.6, we obtain the relationship Vt is equals to V0 in bracket Tt upon T0. Vt upon V0 is equals to Tt upon T0. Thus, we can write a general equation as V2 upon V1 is equals to T2 upon T1, or V1 upon T1 is equals to V2 upon T2, or we can say V upon T is equals to constant, that is K2. So, V is equals to K2T, that T is capital T. The value of constant K2 is determined by the pressure of the gas, its amount, and the units in which volume V is expressed. Equation 5.10 is the mathematical expression for Charles' law, which states that pressure remaining constant, the volume of a fixed mass of a gas is directly proportional to its absolute temperature. Charles found that for all gases at any given pressure, graph of volume versus temperature in Celsius is a straight line, and on extending to a zero volume, each line intercepts the temperature axis at minus 273.15 degrees Celsius. Slopes of lines obtained at different pressure are different, but a zero volume, all the lines meet the temperature axis at minus 273.15 degrees Celsius, and here you can see figure 5.6. Figure 5.6, that is volume versus temperature graph. Each line of the volume versus temperature graph is called isobar. Observation of Charles can be interpreted if we put the value of T in equation 5.6 as minus 273.15 degrees Celsius, we can see that the volume of the gas at minus 273.15 degrees Celsius will be 0. This means that the gas will not exist. In fact, all the gases get liquefied before this temperature is reached. The lowest hypothetical or imaginary temperature at which gases are supposed to occupy zero volume is called absolute zero. All gases obey Charles' law at very low pressure and high temperature. 5.5.3 Galluzak Law, that is pressure-temperature relationship. Pressure in well-inflated tires of automobile is almost constant, but on a hot summer day this increases considerably and tire may burst if pressure is not adjusted properly. During winters, on a cold morning, one may find the pressure in the tires of a vehicle decreased considerably. The mathematical relationship between pressure and temperature was given by Joseph Galluzak and is known as Galluzak Law. It states that at constant volume, pressure of a fixed amount of gas varies directly with the temperature. Mathematically, that is P is proportional to T and P upon T is equals to constant, that is K3. This relationship can be derived from Boyle's law and Charles' law. Pressure versus temperature graph at constant molecular volume constant molar volume is shown in figure 5.7. Each line of this graph is called isochore. 5.5.4 Avogadro Law, and here you can see the figure 5.7, that is pressure versus temperature graph of a gas. Now 5.5.4 Avogadro Law, that is volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusions of Dalton's atomic theory and Galluzak law of combining volumes, that is unit 1, which is now known as Avogadro law. It states that equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. This means that as long as the temperature and pressure remain constant, the volume depends upon number of molecules of the gas, or in other words, amount of the gas. Mathematically, we can write V is proportional to N, where N is the number of moles of the gas, V is equals to K4N, and the number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23 and is known as Avogadro constant. You will find that this is the same number which we came across while discussing the definition of a mole, that is in unit 1. Since volume of a gas is directly proportional to the number of moles, 1 mole of each gas at a standard temperature and pressure, that is STP, will have same volume. Standard temperature and pressure means 273.515 Kelvin, that is 0 degree Celsius temperature, and 1 bar, that is exactly 10 to the power 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter per mole. Molar volume of some gases is given in table 5.2. Here you can see the molar volume in liters per mole of some gases at 273.15 Kelvin and 1 bar. Argon 22.37, carbon dioxide 22.54, dinitrogen 22.69, dioxygen 22.69, dihydrogen 22.72, ideal gas 22.71. Number of moles of gas can be calculated as follows. N is equals to m upon m, where small m is the mass of the gas under investigation and capital M is the molar mass. V is equals to K4 m upon m, and equation 5.13 can be rearranged as follows. M is equals to K4 m upon m is equals to K4D. The previous standard, that is a star point which I am reading, the previous standard is still often used and applies to all chemistry data more than decade old. In this definition, STP denotes the same temperature of 0 degree Celsius but a slightly high pressure of 1 atmosphere. 1 mole of any gas of a combination of gases occupies 22.413996 liter of volume at STP. Standard ambient temperature and pressure, that is SATP, conditions are also used in some scientific works. SATP conditions means 298.15 Kelvin and 1 bar, that is exactly 10 to the power 5 Pascal. At SATP 1 bar and 298.15 Kelvin, the molar volume of an ideal gas is 24.789 liter per mole. Here D is the density of the gas. We can conclude from equation 5.14 that the density of a gas is directly proportional to its molar mass. A gas that follows Boyle's law, Charles' law and Avogadro law is called an ideal gas. Such as gas is hypothetical. It is assumed that intermolecular forces are not present between the molecules of an ideal gas. Real gases follow these laws under a certain specific condition when forces of interaction are practically negligible. In all other situations, these deviate from ideal behavior. You will learn about the deviations later in this unit. In the next part of this chapter audiobook, I will start from 5.6 ideal gas equation Thank you so much, everyone. Take care. Bye bye. Please share with your friends so that they will also get the benefit of these audiobooks. Thank you so much.